Imagine looking up at a flock of thousands of birds. Nobody is giving them directions, yet they are constantly organizing themselves into distinct, tight formations. We face a similar challenge in data science. We are generating massive oceans of unlabeled information, far exceeding the human capacity to manually categorize it. This shows raw information as a computer sees it, a scatterplot of unlabeled black dots. To make sense of this, clustering finds hidden patterns. Shifting right, it partitions the chaotic scatter into distinct colored groups, ensuring objects in the same cluster are highly similar. On the surface, it sounds like a straightforward task, but the true difficulty in clustering lies in how we mathematically define the word similar. This diagram illustrates the k-means algorithm, a popular method that defines similarity through physical distance. It approaches the problem from a geometric perspective, assuming that related data points will clump together around a central point, or centroid. The algorithm uses a simple iterative process. It guesses starting centers, assigns every data point to its nearest center, and recalculates a more accurate center. By assigning, updating, and repeating, the centers eventually lock into final positions. The left chart shows k-means operating successfully, forming well-separated spherical clusters, but the right panel reveals a fatal weakness. When fed complex shapes like interlocking crescent moons, the geometric assumption fails. It improperly slices the data, expecting every group to be compact and centered. The math did exactly what it was told to do. However, because k-means assumes everything is a sphere, we must move beyond simple distance to solve complex real-world data. To solve the crescent moon problem, we redefine the grouping criteria by focusing on connectivity rather than proximity. This similarity graph shows how spectral clustering approaches the data. It models the points as nodes in a network, tied together by weighted edges representing their similarity. Points are connected to their neighbors, creating a web of relationships. This ratio cut diagram shifts the objective toward identifying the mathematical cut that partitions the graph into subgraphs. The goal is to find a balanced slice that severs the weakest connections between groups. This transformation illustrates the bridge to linear algebra, the graph Laplacian. This matrix encodes the entire structure of the node network into a grid of numbers, allowing us to analyze the graph's properties mathematically. Analyzing this matrix allows us to compute eigenvectors that act as a spectral embedding. This process essentially unrolls the data from its original tangled shape into a new representation where the two groups are neat, easily separable blobs. This side-by-side comparison proves the power of using the right representation. By shifting from geometry to connectivity, spectral clustering uncovers the non-convex structure that the original k-means algorithm could not see. Information theory offers an alternative framework, viewing clustering as a pure problem of efficient data storage rather than a map of nodes or points. This funnel graphic illustrates the information bottleneck principle. In this view, clustering is a process of compression. The goal is to squash the raw data into a simpler representation while retaining as much relevant information as possible. This scale models our optimization problem. We are balancing two competing goals. On the left, we minimize the size of the summary to create an efficient bottleneck. On the right, we maximize preserved information to ensure the clusters retain their predictive power. In the information bottleneck paradigm, a successful cluster is defined as the most compressed representation that still preserves predictive power. We have seen different algorithms produce different results based on their specific objectives. This raises a fundamental question. Is there a universal standard or a set of axioms that every good clustering algorithm should possess? John Kleinberg proposed 3 core properties capturing our intuition about how algorithms should behave: scale invariance, richness, and consistency. Multiplying distances by a constant shouldn't change groups. Every partition should be possible, and tightening internal distances shouldn't break existing structures. However, this cracked temple graphic represents a landmark result, the impossibility theorem. Kleinberg proved these properties are in mathematical conflict. Satisfying all 3 simultaneously is impossible. Every algorithm must make a compromise. For example, k-means isn't scale invariant, while other methods fail consistency. Because data is infinitely complex, a singular, mathematically flawless way to group the world does not exist. We can view these three methods as a menu of mathematical trade-offs. Each approach, from simple geometry to information theory, brings a specific set of strengths and inherent biases to the table. Effective analysis requires understanding the underlying structure of your data well enough to know which of these specific flaws you can afford to tolerate. Meaningful clustering requires human intuition to select the right tool for the data, giving context and purpose to the machine's underlying math.